Okay, I already started recording. Good morning, Afif. So which question do you want me to go through? If you just let me know, like, is it the 5A or the 5B, the section A or the section B? I mean, you should have gone through the paper yourself, right? Especially if you're sitting for June 8 as yourself. Anything you want me to go through? It's going to be one-on-one until whoever else show up on time. I can go through anything you want me to go through. Anything at all? You come to the class ready, right? So I hope you come to the class ready. So it's not like your first time in this kind of session. So what do you have to ask? Just about to open your question, is it? Not very nice. Hello, got any question from you, Afif? Hello? Hello? I mean, the session is recording, yeah, Afif. So let the record show that, yeah, what is happening. Hello, good morning, Rahiman. So Afif was doing like one-on-one with me, but he couldn't come up with any question at all for the past 2 minutes like that. So, you know, you have me now. So he's not going to ask any questions, I guess. So, you know, what question do you want me to go through, Rahiman? Just shout out which one you want me to go through, and I'll go through it with you. You can see my screen, right? So there's the organic 5A and then there's the organic 5B. So there's continuation of where we left off last time. So, you know, you just need to tell me which one you want me to go through, and I will be more than happy to go through anything with you. If you don't feel like talking, you can, I don't know, leave a chat message and then I can go through it with you rather than us wasting our 1 hour here. So get on moving. Same goes for you, Isa and Yasmin. If you got any questions, shout out, leave a chat message so that we can get things going. There's no point of me going through questions which I don't even know whether you know it or not, right? So, you know, question better come from the people themselves rather than coming from me. I've never changed the Zoom link as well, yeah? So, you know, everyone should know that we have the same Zoom link every single week, right? So, I don't know. It's already 8:04, 8:05, so let's get moving. What do people want me to cover?
5A.
5A. Okay. Page 8. The whole question?
Yes.
Okay. So this comes under halogenarcane chemistry. When you're in an exam, you cannot expect to say, I don't know how to do the whole question. That means you go in unprepared. Okay. So if you want to think about halogenarcane chemistry, halogenarcane in general go through a couple of reactions, but halogenarcane is quite big in the sense that halogenarcane, they call it RX halogenarcane. So you can have a primary, a secondary, or tertiary halogenarcane. So when you have one halogen and it is bonded to only one carbon, so the carbon bonded to the halogen, the carbon bonded to the halogen is bonded to one other carbon that is called primary. As you can see the primary symbol, 1 degree there, that means the carbon bonded to the halogen is bonded to one other carbon. So if the carbon bonded to the halogen is bonded to 2 other carbons, that is called a secondary halogenarcane. Identifying secondary and primary and tertiary is very important It's the same thing in alcohol. It's the same thing in halogenoalkane. Look at the carbon bonded to the OH, or in this case, the carbon bonded to the chlorine, or in the carbocation case, the carbon with the positive charge. The carbon here with the chlorine is bonded to 1, 2, and 3 other carbon. This is tertiary halogenoalkane. Now, in terms of these, because these are polarized, so these are halogenoalkane, so they are polar, delta minus and delta plus. These are based on the difference in electron negativity. So this thing here, when they form carbocation, this is via heterolytic fissions. There's something called heterolytic fission. This is under introductory organic chemistry, where we break this covalent bond, and we break it such that the electrons go to only one of the atoms. So these are full-headed arrow. They are not half-headed. So that means both the electrons go to the chlorine, and therefore this one will have lost the electron there, and this become a carbocation, and you will get the chlorine with the lone pair fully like that. Heterolytic, unequal, because the 2 electrons go to one species, giving you an anion, giving you a carbocation. This is now a tertiary carbocation. This is related to alkene chemistry. I'll come back to the question a little bit. Yeah? And then when you think about this question here, if you try to do the same thing here, you will get CH3 and then H and H. This carbon with a positive charge is bonded to one other carbon. This is called a primary carbocation. So you know about the stability of carbocation as stated in the AS alkene chemistry syllabus. Primary carbocation is less stable than secondary carbocation, is less stable than tertiary carbocation, because going that series there, going from left to right, the tertiary carbocation have more electron donating groups. These CH3 groups, these are alkyl electron donating groups by inductive effect. This is the same thing when you are asked on the major versus minor products. When you get the carbocation in electrophilic addition mechanism, it's the exact same thing. But here, this is part of a nucleophilic substitution mechanism where this proceeds via carbocations, and this one is a primary halogenoalkane. It does not want to proceed via that. That's because this is unstable. It doesn't have that many alkyl electron donating group. This is good. Electron donating, because this is CH3, this is inductive effect. This is all based on electronic properties. This is donating. At least they can stabilize the positive charge. This doesn't. So if primary halogenoalkane doesn't want to go through this step, how does primary halogenoalkane react? This is via an intermediate. This is called an intermediate. So in terms of the mechanism, there are only 2 mechanisms in this topic, which is Sn1 and Sn2. So your Sn1, as you know from A2 rate of reaction, A2 rate of reaction, A2 kinetics, the 1 there refers to first order, and then the 2 there refers to second order. If you haven't done this topic yet, it is fine, but if you have done this topic, you would know what it means. The Sn there refers to nucleophilic substitution. So the difference there is the first order overall and the second order overall. This is just a bit of A2 stuff. So here you have you have the primary halogenoalkane. And this is, this is tertiary halogenoalkane. This should be tertiary halogenoalkane, Sn1. This to the power of 1. There is no nucleophile in here. That is because in the slower step of the reaction, the rate determining step only has the tertiary halogenoalkane. It proceeds via 2 steps. The first step would be like this. As I have shown you display just now, I don't want to show display again. So it shows you the tertiary halogenoalkane forming the tertiary carbocation, and then you get the lone pair there. Whereas this is only 1 step for Sn2 because you have the primary halogenoalkane undergo Sn2, and that is to the power of 1. That is the order of reaction. And then you have the nucleophile which could be negatively charged but must have lone pair, and then it has power of 1 as well. So both of them order 1 and 1. So you get 1 plus 1 equal to 2. That means 2 molecules are involved in the slow step. There are 2 molecules in the slow step. There is only 1 step in Sn2. It goes direct. It does not want to go through. It does not want to go through the carbocation intermediate, as I've shown you just now. So here, I'm going to draw delta minus delta plus. If you have Sn2 mechanism, it works with primary halogenoalkane. So let me just show using OH minus. I must have a lone pair. The negative charge is not essential because even ammonia can act as a nucleophile, attacks there, and then you break that straight away. So rich attack poor, and then you break the bond. Then you don't stop at the intermediate. Instead, you form the product straight away. So, you just do it in 1 step, and do not forget you also kick out the chloride like that. Whereas the Sn1 proceeded via a carbocation intermediate. This is a tertiary carbocation intermediate. And then we have to try and get to the product because mechanism is from the start to the end. From the start to the end. So from the lone pair, attack the carbons. The lone pair doesn't attack the plus, the lone pair attacks the carbons. And what you get is, you get the product. And of course, you already kick out the Cl minus. If you are asked in a multiple choice questions, how do they ask this? Well, they will ask you in a reaction profile diagram. How does this Sn1 reaction looks like? Well, there will be an intermediate. Intermediate means it's somewhere in between. So it will go via a double harm reaction profile diagram. What have I done here? I have shown the first step has this activation energy. So this is EA1. The second step has this much activation energy, EA2. Why do I show the first step has a higher activation energy? Because the first step is slow. This is slow. This is called rate determining step. If you have done A2 rate of reaction, which I believe either is coming up or it is happening soon in your A2 syllabus, then you will know this is the slowest step in the reaction, highest first activation energy compared to the second step, which is fast. Okay, whereas the other one has to be a single step for Sn2, so there is no intermediate. There's just reactant going to product. It's just a single step. This is a single step mechanism, Sn2. This is a double step mechanism. This is your reactant. This is your product. This is a double step mechanism. So this is your Sn1 reaction. Now, in terms of other chemistry of halogenoalkane, what else do they like to ask you on halogenoalkane? It's basically substitution versus elimination. So I'm just going to show you one example. If this is Br, and then this is H, and then this is H, and H, and H, and H. So what could happen here is, this is definitely a primary halogenoalkane. The carbon bonded to the halogen is bonded to one other carbon, or you can say the carbon bonded to the halogen is bonded to 2 other hydrogen. I usually relate primary with 1. It's bonded to 1 other carbon. That is what I remember. Okay, so 2 things could happen. This is the case study of substitution versus elimination. It's very, very popular in your AS as well as A2 chemistry. So when I do substitution, what do I get? I replace the Br with things like OH, for instance. And then I could do elimination, and then I get a carbon-carbon double bond, and then a H, 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 and of course I kick out HBr. If I want to do elimination, I am eliminating the Br and do not remove the H from the same carbon. I remove the H from the next carbon because I want to get a double bond. So I cannot get a double bond if I remove the hydrogen from the same carbon. For you to be able to do elimination, you must have a hydrogen on the next carbon to the carbon with the halogen. This is an alkene. This is an alcohol. So be very careful what product you are getting. This reaction called substitution has a specific name. It is called hydrolysis simply because you have used OH minus to replace Br minus. But this reaction elimination is also using NaOH, or you can use KOH. But what is very important is the condition. This has to be done in ethanol. Ethanol is the solvent. You have to use ethanol in order to favor the reaction, favoring elimination. On the left-hand side, if you want substitution, you just use NaOH or KOH, but you see it's the same reactant, and the question specified really in the solvent. This is in water, or they will write aqueous. Aqueous mean water, water mean aqueous, and of course you have to reflux that as well. So the key thing there is in aqueous versus in ethanol. Aqueous, hydrolysis in the presence of water. In the presence of water, hydrolysis. In the presence of water, break the carbon-bromine polar bond there. Okay, of course that is polarized, and then the hydrolysis here should proceed via Sn2 because this is primary. If this is tertiary halogenoarcane, it will most likely proceed via Sn1, which is the mechanism I outlined previously. What I've done was I've just gone through quite a few things there. So you won't really get the S plus or S minus in your exam question. So state the type of reaction. Here you get alkene, you see, to produce alkene. So this must be elimination. And then the conditions necessary for elimination. This is not hydrolysis. Not hydrolysis means I do not want water. I do not want water. What I want is in ethanol, because I want to get the alkene. I do not want to get the alcohol. Okay, so they say NaOH because the question said NaOH. So I don't want to use KOH because the question said NaOH. Okay, and then it's reflux as well. You see the conditions mean plural. First condition, second condition, 2 marks. Conditions, read the question, 2 points. Give the display formula. When the question asks you specifically, you have to give whatever the question wants you to give. So what do we have? We have 2 bromobutane. So if I draw skeletal formula, 1, 2, 3, and 4. Again and again, you don't like skeletal, but the question will give you skeletal. What do? You still have to do it, right? So you better get going with knowing your skeletal formula, right? Skeletal formula is elegant and it's nice and simple. So how many hydrogen is here? Let me ask some people. Oops, sorry. Let me ask some people. Afif, how many hydrogen is here?
3.
3. And here, Afif? The mantra is that carbon form 4 bond. Start from there. Carbon form 4 bond. So how many hydrogen is here?
1.
All of 1. And here?
2. 3.
Okay. When you write your skeletal formula, when you write your structural formula, you should be able to do this very quickly because you don't know when the question will ask you structural or skeletal, whatever. They want display, but I wouldn't be working in display because they will waste a lot of time. So what I'll do is I think about the hydrogens on the next carbon. Why do I think about the next carbon? Because I'm doing alkenes, so I'm doing elimination. Elimination means I will reform the double bond. So if I remove from the black color one, I will get my double bond here. So I remove the hydrogen from there. But there are 2 hydrogen according to Afif here. There are 3 hydrogen according to Afif here. So 3 and 2 are definitely not the same. Not the same. And therefore, I will get different product. So if I write this product first, the red color one, I can see no cis and trans. Remember when someone asked me, can you have cis and trans here? You cannot. Why? Because you have 2 atoms or 2 groups that are the same on one side of the carbon-carbon double bond. This is a CH2 double bond. You have 2 hydrogen atoms there, no cis and trans. So very clearly, this is going just to be one product. So carbon there form 2 hydrogen bonds there because carbon form 4 bond, 1 and 2, there are 2 hydrogen. There is 1 hydrogen because 1, 2, 3 bond already. So there's 1 hydrogen and then a CH2, a CH3. So this is 1, 2, 3, and 4. This is called but1-ene. On to the next one. If I go to the black color one, again, you will see what I'm trying to do. I'm trying to work in skeletal. Why? Because it's faster. It's faster. So I remove the hydrogen from the black color one. So my double bond is between 2 and 3. And then you can clearly see now I can have cis and trans. So when I draw display, I can show the cis and trans. So I'm going to show the trans first, and you can see what is happening there. So of course, display every single bond. Some student will make the mistake of miscounting. Yeah. So if you miscount something, unfortunately, it means that you don't know how to count the carbon from 4 bond. So, if you leave it hanging like that, you will have lost the 1 mark very, very easily. So both of them, 1, 2, 3, 4, 1, 2, 3, 4, these are built to int. This is also built to int. The difference comes to the cis and the trans in front. So when on the same side, that is your cis, and this one is your trans there. Okay, hopefully that makes sense. Now you want hydrolysis. Hydrolysis means you are trying to do it in water. So this is NaOH because the question specifies NaOH, NaOH in water, or you can just say NaOH aqueous. Question will not be so obvious to tell you it's in water. Aqueous means in water. So, sometimes questions say NaOH aqueous, it means you are getting hydrolysis instead of elimination, and you have to do reflux as well. Now, what do they want? They want Sn1. So I already shown you the mechanism once. This is a bit tricky because this carbon with the halogen is bonded to 1 and 2 other carbon. This is secondary halogenoalkane. We don't know which way secondary halogenoalkane will go, but they say Sn1, so we follow the question. The first thing we do is label dipole. Oops, I have labeled the dipole incorrectly. The electronegative halogen will be delta negative, this will be delta positive. Follow, yeah? I'm doing this mechanism for the second time now, right? The first step is label dipoles. The second step is heterolytic fission. Heterolytic fission, break the bond so that both the electrons go to the delta negative atom. Then what I will get is, I will get a carbocation. A carbocation is going to be trigonal planar because this carbon there originally has 4 outer shell electrons. Now it has 1, 2, and 3 bonding pair. So 3 bond pairs, 0 lone pairs, because now I only have 0 electrons left because I have a +1 charge. So I don't have 4 electrons. I have 3 electrons around carbon because of the plus charge. So 0 lone pair. The 3 bond pairs repel equally. You get a trigonal planar, and you get 120 degree. And this is a carbon sp2 hybridized center. As you would know, in any carbocations, sp2 hybridization, trigonal planar, just like in benzene as well. So it's flat. What happened then is you get the OH minus, and this one has a lone pair, even though it's the negative charge, but it's the lone pair that's important to show its property as a nucleophile. I also need to show the Br minus getting kicked out, and that's the end of the Sn1 mechanism, where this is the slow step. Rate determining step is the slowest step in the overall reaction. Slower first step, faster second step, Sn1 mechanism. I think the rest of the question shouldn't be that bad. Now this thing, I can assure you, this is more of an A2 question. If you look in the A2 syllabus under organic synthesis, they talk about this optically active. They also talk about racemic. Racemic mixture means 50% of each enantiomer. That is the meaning of racemic mixture. Enantiomers is your non-superimposable. Your mirror images, they are not the same because your carbon is bonded to 4 different atoms. So enantiomers are your non-superimposable mirror images of each other. Now, optically active means it rotates plane polarized light in one direction. So if you think about optical isomers, there is nothing that is different. There's nothing that's different. When you draw CH3, CH2, CH3, and then CH2, CH2, CH3. When you draw the mirror images of it, they just differ in terms of their 3-dimensional orientation, but everything about them is the same. They have the same boiling point, same melting point, same density, same everything, same chemical properties, because they have the exact same groups. Just mirror images, right? So what is different is optical activity. Optic is to do with light, And it is this thing that you might not have heard of, but it is definitely in the syllabus. Yeah, I used to teach this as part of AS chemistry, so I don't know why. I think these days they probably moved it to A2 chemistry already. They rotate plane polarized light. So what happened is when you proceed via a carbocation, such as the one just now, I think it was a H, and then a CH3, a CH2, CH3. Remember you mentioned about carbocation? Carbocation is trigonoplanar. Carbocation is trigonoplanar. It is flat. It is flat. When it is flat, your nucleophile can attack from the top of the plane. Your nucleophile can attack from the bottom of the plane. So that means, do they attack with equal chances? Yes, they do. So via Sn1, the nucleophile can attack with equal chances. They can attack with equal opportunities or equal chances. This is about probability from the top or bottom of the trigonoplanar intermediate. You proceeded via the carbocation intermediate, right? And it was trigonoplanar sp2 hybridization, right? So, you know, as a result of this, you're going to get 50% of the enantiomer where the OH minus attack from the top and give you the final product with 4 different groups on the carbon. Or you can get the mirror images where the OH minus attack from the bottom, and therefore you're going to get a racemic mixture. Racemic means 50% of each enantiomer. You get 50% that rotate clockwise, you get 50% that rotate anti-clockwise. They will cancel out. So optical activity cancel out. This is optically inactive because they cancel out. They cancel out. The rotation of the plane polarized cancel out, even though you have a chiral carbon. That's why you get optically inactive with this Sn1 mechanism, only because you proceed via intermediate here, where you have equal chances of attack from the top or below the plane, carbocation intermediate. The other mechanism give a optically active product, there will be Sn2, because only one product. There's no racemic mixture, because you only do one step. If you think about how Sn2 proceeded just now, it was one step, right? So if it was Sn2 would have gone one step. You don't have that equal chances of attack from the top below the plane because you don't go via intermediate. Therefore, your product will still be chiral. So this is not the correct one because our example just now was based on the secondary halogenoarcane. If we proceed single step by Sn2, you will get an optically active product instead of a racemic mixture. Hopefully that makes sense then. Quite a tricky question, yeah, which is why it's 5 marks. Blah, blah, blah. So now you have 2-bromobutane. So this is 2-bromobutane. Now, if you proceed via, hang on, this one is via Sn1 mechanism. You want a structural isomer. So not this one, not this. This is secondary. So you want exclusive Sn1. So you want tertiary halogenoarcane. So there you go. I have just produced a halogenoarcane, which is tertiary. This is 1, 2, 3, and 4. 1, 2, 3, and 4. This is a structural isomer of this. Okay. In fact, the relationship between this and this, if you see here, this is a longest chain 3 carbon. This is the longest chain 4 carbon. These are what you call chain isomer. Chain isomer, meaning straight chain versus branch chain, is part of structural isomerism in AS chemistry. I don't need to show you the mechanism, but they did say, explain why the mechanism, because you will proceed via the more stable tertiary carbocation, and you will say something about the 3 times alkyl electron donating groups by inductive effect. So this isomer, you can draw it. They don't say give the name, but if you're asked for the name, this one will be 3 carbon, longest chain there. So it's a halogenoarcane, so it's a bromo, it's a 2-bromo, but I also have a methyl group, a CH3 there. So it's 2-bromo, 2-methyl propane, 2-bromo, 2-methyl propane. Okay, and just like that, you get like a really, really long question, which could essentially be the whole organic chemistry question. It's less likely Cambridge or A-level, the international A-level, are most likely to break this down into like 10 marks and 10 marks from another organic chemistry kind of section, rather than giving everything for halogenarcane. But anyway, this is a really good question. Okay, I spent quite a lot of time there now, so there's halogenarcane completed. Any other questions? 5A or 5B? Come on. The more you ask your questions, you get your questions answered. Anything? Hello, hello. Hello, good morning, everyone. Next question. I am waiting.
5B.
5B. Which one do you want me to go through?
4.
Question 4. You know mass spec and infrared. Question 5. This is the question, right? Yep. Okay. So this is about structural isomers. This is the correct question, yeah?
No, yang last.
Oh, yang last one. Okay, that last one I remember. I just added in the very last one because it's to do with, this is from this one, yeah? Okay.
Yes.
So this is from the sample paper 2022. This is new in the AS syllabus. And do you know what year this is in? This is the current year. This is 2022 year. So whatever is in this sample paper, they are trying to show you what your actual June paper will look like. Okay. So what I can tell you is mass spec, including the use of this formula, is now in AS. It used to be in A2, the use of this formula. So in my topical playlist on this particular stuff, I already moved the A2 stuff into the AS playlist. I think it's part of carboxylic acid ester. So make sure you know this is in the syllabus, right? This is called the parent ion. The parent ion is basically the M+. This is called the M+1. Okay, everything in the mass spec has a positive charge because of the x-axis is called mass over charge. If you don't have a charge, if you don't have a charge species, you will not see it. The plus charge is just a formality. The M+1 means the mass number, you have to add 1. Okay, everything there, you have lost 1 electrons in the mass spec for you to be detected. But you know about mass of electron is roughly 1/2000 times the mass of protons or the mass of neutrons. So, you know, it's very negligible, very, very small. So losing 1 electron doesn't change your mass very much, unless you're talking about 3 or 4 decimal place, then you can see the difference. Now, a molecule of X contains 6 carbon atoms. You need to demonstrate that it is correct. This is basically show that N equal to 6. This means the number of carbon. And you're going to show you're working for 2 marks. You must know your formula. I can show you where in the syllabus, so number of carbon is 100/1.1 times percentage of M+1 divided by percentage of M. I always forget this formula. I tell you why, okay? I remember the 100 is to 1.1. The 1.1 is because of 13 carbon. Carbon 13 is roughly 1.1%. Majority of our carbon isotope actually is carbon 12, but we have around 1.1% of carbon 13. I have no problem with this. My problem is always this, okay? Now, I know, indah banyak, I don't have a lot of 1.1% carbon 13, but I have a lot of the parent ion that comes from the carbon 12. This comes from carbon 12. Not a lot of this come from carbon 13. That's why there is an additional 1 unit of mass. So I know this is not a lot, okay? If this is bigger, I multiply by not a lot. And this is smaller, I multiply by a lot. Otherwise, a lot times a lot, and then I will get a big number, which is ridiculous. Okay, that's usually how I know it, okay? But even though if the question doesn't ask you to show, you must be able to know this formula is as stated in the syllabus, okay? Candidates should be able to state this formula from the syllabus and use it. Percentage of M+1 is 6.5%, so just put in 6.5. Percentage of the thing there, relative abundance, 100 there. So I just put in 100 there. So press your calculator. You see the 100 and 100 cancel out. So 6.5 divided by 1.1. I am doing a show that question. I cannot have decimal place for my number of carbon atom. It has to be rounded up to the nearest whole number. Okay, do not leave your answer to decimal place. This is nearest whole number because it is the number of carbon atom. All good there? Everyone has seen the formula before? Can I confirm everyone has seen the formula before? Okay, who has never seen the formula? Can you tell me who has never seen this formula before?
Me.
Who's that? Huh? You never? Oh no, okay.
Yeah.
This is the syllabus. This is the syllabus, okay? The syllabus. Can I ask you to actually go through the syllabus fully? So everything in here is AS. AS, huh? All of this is AS, okay? Now under the AS chemistry, there's infrared. There's infrared. Infrared you should know, right? Ta-da! Number 5. And I will tell you something. This one, it says, where is it? On top here, it says for 2022, 2023, 2024. It starts from March 2022 exam already. Okay, don't say I never tell you. Yeah? Everything in here is AS. It used to be A2, now it's AS. It's no longer an A2. You might want to remind your teachers perhaps, because sometimes teachers can be forgetful. Okay, yeah, but if your teacher is forgetful, you shouldn't be forgetful also. You have the syllabus, yeah. This is called sample paper 2022. Is to remind students what they should expect in the upcoming exam. Okay, all clear now, yeah? Your textbooks, I will share something later on. Okay, I don't want to say it because this is being recorded, but I'll share with you something later on, yeah? Suggest the molecular formula of X. Molecular formula definition means the actual number of atoms in one single molecule. Using this information from figure 5.1, we know we have 6 carbon. We know we have 6 carbon, all right? So this is our parent ion. So we have 6 carbon. We have hydrogen and oxygen as well. So carbon, hydrogen, and oxygen. So 6 carbon is 6 times 12, which is 72. So my target is this 100. So I have 6 carbons. So 100 minus 72, I'm left with, I don't know, 100 minus 72, I'm left with 28. So now I know I must have oxygen because they say I have hydrogen and I have oxygen. Do you think I can have 2 oxygens? Is that possible? What do you think, Yasmin? Can I have 2 oxygens? Hello, Yasmin?
Yasmin punya microphone is not working.
Oh, okay. Rahiman, what do you think? Can you have 2 oxygens?
No.
You cannot have 2 oxygen because 2 times 16 is 32. So you know based on this, after you take away the 6 carbon, you must have hydrogen and oxygen still, but you cannot have 2 oxygen. I cannot have 0 oxygen because must have oxygen according to the question. So not 2, not 0. So what must I have? I must have 1 oxygen, which is 16 times 1 is 16. So just now my difference was 28 after I take away 6 carbon. So 28 minus 16, that means I have 12 hydrogen. Okay, so altogether I must have C6H12, or you can do 12 times 6 plus 12 times 1 plus 16 times 1, and you should get 100. Let me check. Yep, I get 100 exactly. Hopefully that makes sense there. This is what you use mass spec for, yeah? You use it to fragment and suggest what could be the possible one. C6H12O, so C6H12O. So you could get like 2 oxygen, which makes sense, but then suddenly you realize that the mass doesn't add up and it must have 6 carbon according to the question. The next one is called the fragmentation. So what you're doing is you're chopping up the molecule, fragmenting, you basically chop up the molecule. There are a few things that you need to keep an eye out for in mass spec. So obviously we don't have much time, but let me just teach you a little bit of mass spec, okay? So since you already started asking me on mass spec, let me teach you a little bit of mass spec. When you have CH3 like this, and CH2 like that, so what you do is you consider the whole molecule. So the M, this is called the parent ion. The parent ion is basically the whole thing, So you have CH3, CH2, CH3 plus, so this thing, the M over Z or M over E would be 12 plus 3 plus 12 plus 2 plus 12 plus 3. So there's 44. Now I'm going to chop up the molecule. I will chop up at the sensible place. I usually don't chop up the CH, I chop up at the CC. So this thing here is what you call the CH3, and everything in the mass spec is plus. So this thing you will see at 15. But if you chop up this end, you also see this end. So what is this end here? This end will be CH3, CH2, which you could also write as C2H5. It's just that you don't see what is happening now. And this one will be 15 plus 12. This one is going to be M over E of 29. Okay, so when you see M over E of 15, you should think of methyl, CH3. When you think of 29, if you see there's a difference of 29, it means you chop away this thing. If you see a 29, that's because you are seeing this thing here. This and this are the same. It's this fragment. Of course, then if I chop here, I will get the ethyl, and I'll get the methyl, which is the same there. So 15 and 29 is the peak that I will see in this one. Should be pretty straightforward there. Okay. Now I'm going to do something a little bit more complicated. I am going to show 4 carbon. I don't always draw display, you will realize that, but it's important to show display here because we are trying to prove a point with fragmentation. So you will see that I'm drawing 3 carbon there because I'm going to do a chain isomer. These questions will link very well with isomerism. They will ask you what kind of relationship do you have? You must have chain isomerism because structural isomerism, straight chain, branch chain. They can also ask you a bit of naming. This will be called butane. This will be called propane because the longest chain carbon is 1, 2, and 3. And you have a methyl group at carbon 2. This is called 2-methyl propane. Now, what is the difference here? Well, I cannot tell the difference. One thing is I can tell the difference in terms of boiling point. So you will see that this is straight chain. If you have 2 pens which are straight, like the pen you use for writing, the pen can get close to each other. They can get close to each other, so the van der Waals is stronger. And that is because the surface area is bigger. So you can get close to each other. This is van der Waals. So the boiling point will be higher. So if you try to do distillation, fractional distillation of this will come later, this will boil first. And why is it? Well, if you are branch, you cannot get as close. Cannot get as close. If you cannot get as close, that means, branch chain cannot get as close. So that is due to the surface area being smaller. So it is more branch. So the surface area is smaller. So the boiling point, well, actually I should talk about the van der Waals first because we always talk about intermolecular forces. The van der Waals will be weaker. The boiling point will be lower. Apart from that, what can I do? Rather than checking out the boiling point, what else can I do to tell the difference? Well, there is nothing in the infrared that can tell me the difference because there's no signature kind of infrared stretches. So infrared is not very useful between this and this. Infrared is not useful. What is useful is mass spec. Okay, mass spec. So I'm gonna work out the molecular ion peak. That means total up the whole thing. 4 carbon, 10 hydrogen. The M over E is going to be 12 times 4 plus 10 times 1. That's just 58. I will see 58 for this. I will see 58 for that as well. So both of them, I will see 58. But what is different will be when I start to fragment it. When I start to break them, what difference will I see? Well, I'm going to chop this end up. So I'm going to chop up the CH3. When I chop up the CH3, I of course will see CH3 plus, then there will be 15. But I also see the other end, which is 3 carbon. And I have 3 hydrogen, 6 hydrogen, 7 hydrogen. And this will be 58 minus 15 because, this minus this give me the other part of the molecule. This is 43. So just now you have 15. You also have 29. And how do I get 29? Let me show you. If I chop this end up, so this end is the same as that end, is C2H5. So you get C2H5. Or you can write CH3CH2. Everything in the mass spec has a plus charge. It does not mean your mass is plus. It simply means you have lost an electrons. Okay. So 12 times 2 plus 5 is 29. These are some numbers that you need to keep an eye out for: 15, 29, 43. Okay. Anyway, so that much is pretty much done there, because when I chop further, I'll get the 3 carbon N there and 1 carbon N, which is the same as that. So I will get 58, 15, 43, and 29. Okay. So what do I get here? Here is slightly different because of the branching. I can chop that. Then I will get CH3, which will be 15. I put a square bracket there, by the way. And then when I fragment this side will have the 3 carbons and 7 hydrogens. So I also see this. So I also see 43, which is the same, that and that, that and that. But what else do I see? Well, I could also see the one where I fragment there. So you will see that the pink color one, which I fragment there. Is this correct? Is this correct? Okay. So if I fragment that and then, if I just fragment them, I will get a peak at C3, oops, sorry, C4, H9. So this one will be 57 because I've just, fragment the CH there. Because of the branching, you will see that, what else can I get? I can also branch when I lose from there and when I lose from there, so that I just get this end here. So I will get CH3CH, which is the same as C2H4, and that will be 24 plus 4, there'll be 28. I don't think you can get 28 here. You can never get the 28 here, but you can get it there because you can kick out the CH3, you can kick out the CH3. I should probably not go for this minus H because usually we don't break that, but this one should be characteristic of this branch alkane here, the chain isomer. So hopefully that should make sense there. But that's just, a bit of flavor into mass spec. We're going back to our original molecule. Suggest the molecular formula of the fragment. You see, this is the fragment, not the whole thing. At 31. 31 is one of those special things. What did I say just now? The CH3 is 15. The CH3CH2 was 29. The CH3CH2CH2 was 43. I want 31. I am thinking about the oxygens, which is 16, and I'm thinking about 15. I'm thinking about 15, which is CH3. This is most likely to be CH3 or like that. Hopefully that makes sense there. Because, CH3 is very easily chopped off, but 15 plus 14 is 29. I do not want to give this, all right? You might be thinking about CH3, like H, like that, 15, 15, and 1. You do not chop up randomly. You also have to consider the molecular formula itself also. So usually I wouldn't go for things like this, okay? So just go for some sensible one, which also include the heteroatom. Hetero means something different other than the carbon and the hydrogen as well. And one thing you must notice is state suggests the. The means they're looking for one specific thing. There is something specific they are looking for. If they say suggest a molecular formula, that means, it could be more than one option. So this is just coming down to reading and interpreting the question. Hopefully that makes sense there, yeah? You will no longer be given a data booklet. So when you are given an infrared question, the data will be inside the question itself. No more data booklet, yeah? Whatever you're used to finding the data booklet, now everything is in the question. They might already have taken out some data from the data booklet. Like those atomic radii, ionic radii, please don't expect them in the data booklet anymore. You will not get them in the exam anymore. Okay, if you don't know your atomic and ionic radii across the third period, you gotta know them, okay? I'm pretty sure those will come out. Now this is 1 mark. Identify the functional group present in X. Give a reason. So a lot of students, they say, I already answered the question. Well, you might not answer the question correctly, or fully. So using your answer in B, what was your answer in B? Your answer in B was C6H12O. C6H12O. So we have C6H12O. So we must have carbon-carbon, we must have carbon-hydrogen, we must have carbon-oxygen, we must have, do we have OH? That's the question. Do we have OH or do we have C double bond O? That's the question. Do we have OH or do we have C double bond O? Well, we can see this is the OH region. This is broad, and this is strong. The strong refers to they have a strong absorption. The broad refers to they are not sharp. This is sharp. So you see how narrow it is? That is called sharp. This is broad. Okay, they are broad. And then there is something else that's missing. So around these regions, around the 1700 to, I don't know, 1900 or 1800, this is not being specific, yeah? This is just being general. And you should know this region, this thing has a wave number. This thing, CO, is around the 1600 to 1800 region. So again, I'm not being very specific because these are daytime questions. You have the OH there, which is around 3000 to 3500 wave number. So these are strong, broad absorption. They don't describe it there, but characteristic is around there is strong, broad absorptions. There is OH. So OH is present, but C double bond O is not present. Okay, don't say it's present. There's nothing there. This thing is way below the C double bond O region. There is nothing in the C double bond O region. You have OH, but this is functional group. They want you to specify functional group. So OH can be carboxyl or could be hydroxy. I don't think you will have identified the functional group and information from the 5.2 and 5.1. 5.2 and 5.1. Okay, now do you have C single bond O? There's the question. If you don't have C double bond O, do you have C single bond O then? Well, we could also be looking at hydroxy ester 1040 to 1300, 1040 to 1300. I think this is your CO. Okay, so identify the functional group. So we have CO. They are not asking for bonds, yeah? I'm just going to write down the bonds present. The CO at around 1100, at around 1100 wave number, and OH at around right in the middle. This is 3000, so 3300 maybe, 3300 maybe. And what do I have now? I cannot have a carboxyl. Carboxyl means COOH, but then I do not have CO. I do not have C double bond O according to my analysis just now. So this must be a hydroxy group. Hydroxy group. So what do they want? They want a functional group. So functional group must be hydroxy according to the question there. Okay, so hopefully that makes sense there. So you don't have C double bond O, cannot be carboxyl, but you have OH and you have C single bond O, so must be hydroxy. So that's my reason there. No C double bond O. All right, there's the end of that question. Okay, next question. We have around 7 minutes, so I better go through as much as I can. Any other questions? Come on, chop chop. Anything else? Hello, people are still there? Actually, before we end, why don't we need a quick attendance photo, right? So let's just turn on our cameras and take a quick photo before I forget. Hopefully people are still awake. So you know you have to go through your syllabus, yeah, people. Okay, smile, you're on camera. 1, 2, 3. Let's just take one more. 1, 2, 3. Oh, good. Okay, so let's get back to, let's just stop the video and let's just get back to, probably have time for one last question. So come on, anything you want to ask me? So this is the last week we'll do organic chemistry, yeah? So it will be your AS coming up soon. You have to consider that there are other things besides organic chemistry. There is inorganic chemistry, there's physical as well. We spent quite a bit of time on the physical side at the beginning of the year when we did through all those small calculation stuff. So I thought it'd be quite nice to go through inorganic chemistry. I'll post up some questions later on, maybe not today, maybe tomorrow. And again, the job is on you to go through the syllabus, and you can tell me what you really want me to go through, you know, after you go through the question. It's not enough just to do 1 or 2 paper and say, oh, okay, I'm good. Okay, you will realize that if you don't go through the syllabus, you can't blame anyone. Yeah. Okay. Anyway, next question. Come on. 5 minutes is precious. Like I said, I already been here since. 5A or 5B? 5A or 5B?
5B
Yep.
plus part B. 5B.
Hey, oh, there's part B as well. Okay, I didn't see part B. Okay, sorry. Okay. Oh, actually, it's actually a separate question, but anyway, it doesn't matter. I purposely added in some mass spec question because I knew this was new in the syllabus, all right? So this is related to that M plus 2. This is for halogen. This is when you want to identify halogen. So let me just get through this as quickly as I can. So when you have halogens, you can have chlorine 35, chlorine 37. This is 3:1 ratio. This is your AS case study. And that is why they're related to your AS atomic structure and AS mass spec now. This is now also in your AS case study as part of mass spec is 79 bromine is to 81 bromine is 1:1. And you know this because the relative atomic mass given in the data booklet, well, in a periodic table now, no more data booklet, is around 80. So it's somewhere in between. That's because you have roughly, it's around 49.9 something. So it's roughly 1:1. But this is roughly 3:1. Well, this is exactly 3:1. This is roughly 1:1. Okay, so when we get bromine and chlorine, so when you get M:M plus 2, so this is no longer talking about carbon. This is talking about halogen. So this is talking about halogen. The question is, which halogen? Well, you have to compare the height, compare intensity, compare intensities. So M and M plus 2 is a difference. It's a difference of mass unit by 2. So this is no longer M and M plus 1. The one just now to work out the number of carbon, no longer that, yeah? So what happened is you compare the intensity, and to do that, you need to know chlorine 35 is to chlorine 37 is 3:1, but 79 bromine is to 81 bromine is 1:1. So if you have M plus 35 chlorine is to M plus 37 chlorine, your intensity will be 3:1. That's it, okay? So do you have 3:1 intensity height, or do you have 1:1 intensity height? That's the question. So if you look back at your question that had that thing there, so this is talking about 1 bromine, yeah? If you have 1 bromine in your molecule, that means you will have 1:1 intensity like that. Let's have a look at this. We were told about isomeric halogenoalkane, Halogenoalkane. In your AS level chemistry, it could be chlorine or bromine. They don't ask you iodine, okay? Now have a look at this. This is around M:M plus 2. M:M plus 2. What happened then? You see that they are 1:1 height, 1:1 height. So what does this suggest to you? Cannot be chlorine. If it is chlorine, it will be 3:1, but must be bromine, 1:1, because 79 bromine is to 81 bromine is 1:1. Isomer 4 is the isomeric halogenoalkane. So again, we see this trend, 1:1. It cannot be chlorine, must be bromine. Okay, hopefully that makes sense there, yeah? And your job is to think about, can it be 1 bromine or 2 bromine? 79 or 81, when you have 2 of them, it's already exceeded. You already exceeded the mass. So mesti satu saja, only one, cannot be 2, only 1. So when we look at that, 80 plus 81 plus 81 is 160 something. So you only have 1 bromine, which means you must have carbon, you must have hydrogen as well, because they talk about halogenoalkane. So your job now is to work out the formula. So if I look at that, the lower value one, that is 122, sorry, 122 is that, 124 is that. So this is the M, and the other one is your M plus 2, okay? I know it's time already, but let me just finish this thing very quickly. So you have 1 time bromine. So let me use 1 time bromine 79, 1 time 81 bromine. So 122 minus 79 is 43. And you should be able to identify 43 as CH3, CH2, CH2. plus, like I told you earlier, so 3, 4, 5, 6, 7. So you must have C3H7Br. And guess what? 3 carbon halogenoalkane, like that. You only have 2 possibilities. So this question really is a very simple question. Just talk about the 2 different things there. You have 1 bromopropane, and you have the other one, which is 2 bromopropane. So what I want you to do in your free time is to think about fragmenting this. It's easy to fragment the Br, and then you will get that. But your job really is straight chain versus branch chain. Look for the fragmentation. Look for the fragmentation there. Easier thing to do is look at that. Look at the fragmentation there, and then look at the fragmentation there and decide which one is which one. Okay, I'll see you guys next week. So take care, and I better let you go before the next session. You're led to the next session. Okay, bye-bye, everyone.
Thank you, sir.
Thank you, sir.
Thank you. Bye-bye.